Hi guys, myself Dr. Sujatha. Welcome to today's session of Design and Analysis of Algorithms. In this session, we are going to discuss about performance analysis. Nothing but how to analyze the space complexity and time complexity of an algorithm. Performance analysis of an algorithm involves measuring the efficiency of an algorithm. The main goal of performance analysis is to evaluate how well an algorithm scales with increasing input size, and it is used to identify potential bottlenecks or areas for optimization in the algorithm. Performance analysis can be done in two ways. One is posterior analysis and other one is priori analysis. Coming to posterior analysis, this involves analyzing the performance of an algorithm after it has been converted into source code. Initially, we have written an algorithm which is to be called as pseudocode. This pseudocode can be converted into source code by using some programming language. If we analyze the performance of an algorithm after it has been converted into source code, then that analysis is called as posterior analysis. Since this analysis is based on the actual code that is executed by the machine, posterior analysis is machine dependent. And this analysis can help identify issues with the source code that were not anticipated during the priori analysis. This can help improve the code and the overall performance of the software. But however, the performance analysis can be more time consuming and required specialized tools or technologies to analyze the performance of the code. Coming to priori analysis involves analyzing the performance of an algorithm before it is converted into source code. Priori analysis can be done before converting the algorithm into source code. Priori analysis can be done manually without the use of any specific programming language or technology. Thus, it is machine independent. Priori analysis in software development can help identify potential issues with the algorithm and develop strategies to address them before converting it into source code. This can save time and effort in the long run and can help improve the overall performance of the software. The analysis of an algorithm can be analyzed in two terms. One is space complexity and other is time complexity. Now we are going to see how to analyze the space complexity and the time complexity of an algorithm. First of all, what is space complexity? The space complexity analysis involves measuring the amount of memory an algorithm requires to solve a problem as a function of size of its input. This space complexity can be represented the sum of two components. Those two components are fixed component and variable component. Now, in our computer programming, the fixed component refers to the memory space that is allocated for the non-changing parts of a program. It includes several types of memory components such as instruction space, space for simple variables, fixed size, space for fixed size component variables, and space for constant variables. Now, what about all these components? What is instruction space? What is space for simple variables? What is space for fixed size component variables? And what are the constant variables? Here, the instruction space refers to the memory that is reserved for storing the instructions of a program. And the space for simple variables means this includes memory allocated for storing simple data types such as integers, real values, Boolean values, etc. Fixed size component variables refers to the variables that have a fixed size and are used as part of large data structures such as arrays, structures, etc. Constant variables are variables that are assigned a fixed value and cannot be changed during the execution. So finally, the fixed component can be represented as instruction space plus the space for simple variables plus the space for fixed size component variables plus the space for constant variables. Coming to variable component, the variable component refers to the memory space that is allocated for changing parts of a program. It includes several types of memory components such as variable sized component variables, referenced variables, recursion stack space, and data structure components such as linked lists, heaps, trees, graphs, etc. Now, what about these different components? Variable sized component variables refers to the variables that have a size that can change during the execution of program, such as dynamic arrays, dynamic strings, etc. Referenced variables are variables that are used to reference other memory locations, such as pointers. Recursion stack space refers to the memory space that is used to store information about the current state of a function when it is called recursively. And coming to the data structure components, such as linked lists, heaps, trees, graphs, etc. These are composed of multiple nodes or elements, each of which requires a memory space to store the data that they contain. So, finally, the variable component can be represented as the space per variable sized component variables plus the space for referenced variables plus the space for recursion stack plus the space for variable data structure components such as linked lists, heaps, trees, and graphs. So after finding the fixed component space and variable component space, by adding these two spaces, we will get the space complexity. That is, the space complexity of an algorithm A is equal to fixed component space of A plus variable components space of A. Now, we will see an example how to find the space complexity for the given algorithm sum. Here you can see in this algorithm, there are three simple variables. Those three simple variables are result, count, and size. So the total space required for these three simple variables is 3 words. Let us say each variable takes one memory word of space. These three takes the 3 spaces. And the variable components, the array number, which is a variable sized component variable. This array size is depending upon the variable count. We will take the count value from 1 to size. Based on that 1 to size values, that is 1, count initially takes 1. The array size is at that time number of 1, that is 1 value. If count takes 2, number of 2, that is array size will be varied. Like that, we are taking the array size up to size. The size value may be 10 or 20 or 50. Based on the size value, array size varies. So that's why it is to be called as variable sized component variable. So if the size value is n, the array size becomes n. So the space required for storing that array is n. So the fixed component is represented, the space for fixed components is represented with 3 units. The space required for variable components is represented with n. So the total space complexity is that constant 3 plus n. So if I want to express it in terms of notations, it can be represented as big O of n. Coming to the time complexity how to represent the time complexity of an algorithm. The time complexity analysis involves measuring the amount of time an algorithm takes to solve a problem as a function of its input size. The time complexity can also be represented in two terms. One is compile time and other is runtime. So the time complexity of an algorithm A is equal to compile time of A plus runtime of A. The compile time doesn't depend upon the instance characteristics. It can be considered as a constant. Whereas the runtime is denoted by TP, which depends upon the instance characteristics. Here, what is meant by instance characteristics? Instance characteristics is nothing but the size of the input, various operations that we are using in that algorithm, and various kinds of statements, conditional statements, looping statements, what we are using in that algorithm. So the runtime can be represented for finding the operations. The runtime which requires for operations can be represented as TP of operations is equal to, here this is the runtime. Here generally the TP represents the runtime for a particular application or a particular algorithm. Runtime contains instance characteristics, that is input size, various operations, as well as various statements. Runtime for operations can be represented as A into add plus S into subtract plus and so on. Whatever the operations that we are using in that algorithm, those operations can be represented. Here, add function, this add function represents how much time it takes to do that addition operation. And here A represents how many such operations are there. Subtraction represents how much time it required for subtraction. And S represents how many such subtraction operations are there. Like that, for all the operations what we have, we can find the time complexity. So not only the input size and operations, various statements what we are using, those statements also impacts the time complexity. The statements such as conditional statements, looping statements, comparisons, etc. So to keep track of these statements time complexity, we'll use a variable named step count. This variable starts at 0 and it is incremented by 1 at each time the algorithm statement is executed. Here you can see an example algorithm for which how the step count can be calculated. Initially, at the starting of algorithm, the step count value becomes 0. Here S is the Initially, we are using a variable S. We initialized that value. The execution of that statement, by the execution of that statement, the count value is incremented to 1. Now, for I is equal to 1 to n, that is here for loop is opened. So, the opening of for loop will be done for n times. That is, the count value here is incremented for n times. That is, for I is equal to 1, for loop opens 1 time. For I is equal to 2, the for loop opens again second time. For I is equal to 3, the for loop opens again. For I is equal to n, the for loop opens. That is, the count value here is incremented for n times. So initially the count is 1. Initially it is 0. After one statement it becomes 1. Now it becomes 1 plus n. Now here S is equal to S plus A of I. This statement is also executed for n times. So the count value is incremented for n times again. So this is 1 plus n again plus n times, which becomes 2n plus 1. Now for loop is closed. The closing of for loop will be done only one time. Whenever the I value reaches to n, at that time only the for loop closes. One time it will be closed. But for loop opens for n times. right? Now, for closing of for loop, it will be incremented for one time, 2n plus 2, and return s. This return statement can be executed for one time. So for that, the count value is incremented for one time. It becomes 2n plus 3, right? Now here, total time complexity is equal to how I can represent the time for compile time, which is represented as a constant, the time for operations. Here we are representing all addition operations. I'm representing that all these addition operations takes 1 unit of time. And here this is step count, 2n plus 3. This total algorithm executes for 2n plus 3 statements. So totally these two can be considered as constants, and these 3 also can be considered as a constant. And the time complexity is identically can be represented with a big O notation as big O of n. This represents the space and time complexities of an algorithm. I hope that you all understood how to analyze the algorithm's space complexity and time complexity. In our next session, we are going to see asymptotic notations. Thank you for listening.